Hey, so today I'm going to be talking about physical methods of biochem, week of 125. There's 6 topics we're going to be talking about today: Beer's law, uncertainty versus standard deviation, buffers, DNA and nucleic acid structure, ribosomes, and fluorescence. So let's get into it. This week for Beer's law, we talked about Beer's law a lot last week. So this week, all we really did was focus on the uncertainty in Beer's law. Now, for Beer's law, there's a couple different things that can happen. Say they give you the uncertainty of just the extinction coefficient. Well, then what you could do is you could find the range of extinction coefficients and then plug the bounds of that range into E and then find the range of concentration or protein as a result of that. That's one way you can do it. And you can get that for either A or L as well. But the best thing that you can get, the best case scenario, is if you get uncertainty in every single thing. So if you get uncertainty in absorbance, the extinction coefficient, and the path length. Because in that case, we can do something that was it's very reminiscent of what we did in physics lab, right? Where essentially we find the change in the concentration of protein based on the change on each individual component. And we do this by finding the derivative of each component, um, or find the derivative of the concentration of protein dependent on each individual variable. In the case of Beer's law, it's pretty standard, so I will just write it here now. But just to get this, all you have to do is just find a ton of derivatives and plug it back into that original equation. So being something like, oh, sorry, being something like this. So best case scenario, that is the uncertainty that we'll get for Beer's law, and we'll be able to actually use this formula. Now, what's the difference between uncertainty and standard deviation? Well, let's talk about when we would even get standard deviation. We would get standard deviation when we use what's called replicate measurements. What replicate measurements are is it's just the repetition of measurements. So say you just find the measurements of something like 5 times. Well, the replicate measurements would be all the measurements that you got. And then with this, so say you were trying to find concentration of protein, right? And you found that was like 15.17 micrograms per milliliter. And then the next time you tried, you got like 15.21 micrograms per milliliter. And then so on and so forth. That's what a replicate measurement is. Well, if we do replicate measurements, then we would find standard deviation, where standard deviation is equal to the square root of the summation of each individual x term minus the average x term, and that's all squared over the number of measurements you did minus 1. Now, what exactly is standard deviation? Well, standard deviation describes how much the values in a data set differ from the mean. How much the values in a data set differ from the mean. And using standard deviation, we can find what is known as confidence limits. And what a confidence limit is it shows how confident, or it shows what range your next measurement should be within some bounds. Measurement should be. Okay, and this is a slightly different formula, but basically you have your confidence limit is the average of all your measurements plus or minus t, where t is found on a table. I'll show you that in a second. Times the standard deviation times the square root of the number of repetitions you did. Now let me go ahead and find that real quick, that table real quick. Show you what it is. So essentially, if you're doing a confidence limit, you would look at, I'm waiting for this to catch up. Okay, cool. You would look at a table that looks like this, and depending on how confident you want it to be in your next measurements. So say I want it to be 95% confident, then I would use a T from this range, right? And also, you have to select it depending on your degrees of freedom. So remember how degrees of freedom work? It just V would be equal to the number of measurements I did minus 1. So let's say I did 4 measurements and I wanted 95% confidence for my next measurement. I'll just come over here and look at this term. And this is the number I would plug in for T. Okay, cool. Let's talk about how these are different then. So these two are different is because confidence limits and replicate measurements, standard deviation, are going to show you what your next measurement should be. Whereas uncertainty shows you how uncertain you are of your individual measurements. So they are similar, but they're not the same thing by any means. So just keep that in mind when you're doing these kinds of calculations. And also keep in mind, you need to report uncertainty with all numbers, because all numbers in a lab are uncertain. Okay, cool. Next, let's talk about some buffers. Okay. So there's a general idea for buffers, and this isn't specific to biochem, but it says just that weak acids are good buffers, near their pKa values. Or sorry, are good buffers near pH around their pKa values, meaning it should be within 1 to 2 pH units of their pKa. Now, this is something that we learned in Gen Chem, and it's also something that we've seen time and time again with Henderson Hasselbalch. But with biochemistry, it's a little bit different. We don't just use buffers that follow this general rule. We use buffers that have a set of rules, and they're what is called good buffers, and it's from a paper from 1966. But essentially, it defines properties of good buffers, and I'll show them to you now. So properties of good buffers. And they're called quote unquote good buffers because one of the scientists' names was, I think, Norman Good or something like that. Yeah, Norman Good. Okay, so our first property, we want a pKa be around 7. Next, we want it to be compatible with common biochem ions, like magnesium 2+, for example. Next, we don't want it to absorb. So don't absorb light at a wavelength of between 240 nanometers and 400 nanometers. And as you'll recall, we usually measure absorbance at 280 with UV spec. So that should check out. All right, the next thing, we don't want it to absorb, so it doesn't absorb visible light. Which should make sense, especially with the Bradford assay and the BCA assay. Okay. We don't want it to cross membranes. That could be bad for biology. We want them to be stable and cheap. And lastly, we want it to be very soluble in water. Now, it's important to note that there is no buffer that's perfect for every single. There's no buffer perfect for every application. So you can't just use one buffer all the time. You're going to have to change it up. But there are a couple buffers um, that are pretty popular in biochemistry. One of them is known as heaps, and it has the following structure. All right, and here's the structure of heaps. And just to show a couple other good buffers, here's just a couple. So we have MES, tricene, and tris for an example. And just to attest to the point that I was saying before that not one buffer is gonna be good for every case scenario. I just included that tricene will react with flavins. So if you have a compound with flavins in it, then obviously you should not be using tricene. You should choose a different buffer. Okay, cool. With that, then we can move on to nucleic acid structure review. Okay, and here's the structure of a nucleic acid. So as you will notice, for every one base, for every one base, there's a -1 charge. So -1 per base. That's a pretty important thing. And also an important thing to highlight is this phosphodiester bond connecting all of the nucleic acids. Phosphodiester bond. And one last thing that's important about these bases is that G and C will triple hydrogen bond, and A and T will only double hydrogen bond. One other thing that I didn't put in here was that there's an H if this is a DNA, but if this is an RNA, then there's an OH here. And if this is an OH right here, this is part of the reason why RNA is so fragile, is because there's an OH right there, and hydroxide can come over, grab this H, which will make this oxygen right here way more reactive. So what will end up happening is it will attack that phosphorus, or that phosphorus, and you'll end up getting a coordinate that completely breaks the RNA, which again is the reason RNA is so unstable. Okay. Um, So an important thing about double-stranded DNA and RNA too is that it absorbs light at about 260. So DNA and RNA absorbs wavelength at about 260 nanometers. So that's really cool. We can measure DNA and RNA. Another interesting thing about this though is that if we add a nuclease, so if we start to unzip our double helix, and we just have one strand on one side, one strand on the other, then the absorbance will actually increase twofold. Now, this is because without base stacking, the the extinction coefficient will increase. Now recall that pi electrons interact with photons. These pi electrons interact with photons, and the electron will go up into the excited state, so the pi star state. And again, this is really similar to fluorescence, which we'll get into a bit later. But it'll go up into this pi star state. Now, recall that the extinction coefficient is related to the probability of electronic excitement. So the probability of electronic excitements. So, and this probability of electronic excitement depends a lot on the microenvironment. So it depends on microenvironment. Now, believe it or not, water surrounding these nucleic bases actually increases the probability of electronic excitement. So when we denature our protein, we turn it into when we denature our DNA or our RNA and turn it into two strands, then each base is going to start to become surrounded by a water molecule. And if each base is surrounded by a water molecule, then each probability is going to go up. And if each probability of electronic excitement goes up, then that means we're going to be absorbing a lot more. So, um, when there's no stacking, the absorbance can increase like crazy. And we can actually use this phenomenon. It's what we call detecting melting of DNA by hypochromism. Now, what you would see on a normal just absorbance graph, where we're at absorbance of 260, and there's just temperature on the x-axis, what we would see is something that looks like this, where it kind of looks like a titration curve. And this Tm is where the strands start to split apart. Now, generally, though, when you see this stuff in papers, it won't be of this graph. It'll be a derivative of the absorbance. So we'll look a bit more like this. We have dA, so the change in absorbance at 260, depending on the temperature, with temperature on the x-axis. Oh, whoops, sorry. And it'll look something like this. Pretty close to 0, it'll spike up, and then it'll come back down, pretty close to 0. Then the spike is melting temperature. Now, this is huge when base stacking is interrupted. Now, a bit of a caveat now. Let's talk about the Turner rules. Let's talk about the energy based on what nucleophilic bases we have. Or not nucleophilic, sorry. What nucleic acid bases we have. Just doing some biochem stuff. So we have AT and GC, where AT forms double bonds or double hydrogen bonds, and these form triple hydrogen bonds. Well, you would think possibly that no matter the sequence, these bases would have the same energy, but this is not the case. And this is what's known as the Turner rules. So the Turner rule. What this says is that not all AT and GC bonds have the same energy. What's the reason for this? Well, if we look at a base, so let's just look at this base. So as we look at this base, what you can see is that there's definitely going to be areas where there's partial negative and partial positive charges, because some of these bonds are polar, right? Especially with these hydrogens directly attached to a nitrogen. These nitrogens are generally going to be negative throughout the entire molecule, right? And pretty much most of the hydrogens will be positive. So what we end up having is we have areas of charge that are negative and areas of charge that are positive. So if we can get areas of positive charge, so we get our partial positive and our partial negative charges to line up, within our DNA, or RNA, then what we get is we get more stabilization with dipole interactions. But that is why they change. It's not an insane amount of change. It's a lot, but it's not insane. So like the strongest is if I have GC, CG. That is the strongest one. It's minus 14.59 kcals per mole. And then the smallest one is ATTA with minus 3.82 kcal per mole. So again, it's not an insane difference, but it is large enough that we definitely can't ignore it. Okay, cool. Well, let's continue on here. So talking again about hypochromism, there is a way that we can use formulas in the Van Hoff equation to find the roughly the change in enthalpy and the change in entropy. So let's talk about what equations those are. So first we can find the fraction of unfolded. So fraction of unfolded RNA with the following equation. Or sorry, unfolded RNA at some temperature, where we have the absorbance at 260 times the temperature minus the absorbance at 260 minus the minimum absorbance over the absorbance at 260 max minus the absorbance at 260 min. This gives us the fraction of unfolded. And what we want to look at is we want to look at the fraction unfolded, so unfolded over folded, where really we're just assuming that this is just a one-step process where it's either folded or unfolded. This is actually one of the downfalls of this, but we won't get into that just yet. Okay. So now if we can find KEQs at a lot of different spots, then we can find something using thermodynamics. So thermo. If you use thermodynamics, if we incorporate the Van Hoff equation, which is ln KEQ is equal to the negative delta H over R times 1 over T plus delta S over R. If we incorporate this equation, since we already know our KEQs and we're changing the temperature, then we have our dependent and independent variables. We can set up a graph. So let's go ahead and do that. So we have ln KEQ as the dependent variable, 1 over T as the independent. What we have is if we get a line, say something like this, then our slope is going to be the negative delta H over R, where R is the gas constant. And then our y-intercept is delta S over R. So we'll be able to find everything we could want from this equation. There are some downsides to this. Let's talk about some of those disadvantages. So one disadvantage is that it's only approximate. It's only approximate delta H and delta S. And it also assumes it's a simple two-state transition, which isn't always the case. But there are some advantages to this one as well. And really, it's just fast, it's easy, and you only need a small amount. Now there is an alternative to this, which we haven't learned yet, but he has mentioned, called calorimetry. We'll get into that later. Not this week, though. Right. Now I just need to mention a couple more things, and I think we're pretty much done. So he did mention ribosomes this week. Recall ribosomes catalyze, or really, they catalyze the transition of mRNA to protein. They are like the factories that make proteins. So ribosomes are made up of a third of their mass is proteins, and 2/3 of their mass is RNA. It's rRNA, where R, the little r, stands for ribosomal. Now, when looking at these ribosomes, one notices that there are some popular sequences, such as UNCG, where N is any kind of base, and then G in RA. That's also a popular one. And the reason that these are so stable, or these are so popular in loops, is because they form H bonding networks, which not only makes them really stable, but it also causes them to turn inward and again form that loop. Now, one loop that we see a lot is a tetra loop structure. We see a tetra loop a lot because it can form a lot of hydrogen bonds. It forms, and it's incredibly stable. So, um, so yeah, this is pretty. It's very similar to this in this way. All right. Lastly, when observing RNA and observing RNA, what you want to do is you want to observe it in a slightly acidic environment to um, prevent base catalyzed um, hydrolysis. Because remember that RNA is very susceptible to it with that hydroxide group on it. And then also you want to react with EDTA. Now this is a compound that um, binds magnesium ion, which is a catalyst for RNA hydrolysis, as well as some other ions that really get a chance to see yet. Okay, cool. Now the last thing we're going to talk about is fluorescence. What is fluorescence? So fluorescence, I'll give you a formal definition here, is the absorption of a short wavelength, um, either UV or visible light. Um, and then it's followed by the emission of a photon, of a longer wavelength photon. All right, cool. Fluorescence is very appealing a lot of the times because it is very sensitive. It's incredibly sensitive. In fact, it can even detect one molecule, um, a single molecule, and you compare that to a Bradford assay, which can detect a microgram per milliliter. That's insane. That's that's factors different. So that's one reason why it's so popular. And the reason that this method can detect with such sensitivity is because if we're looking at, say we have our setup, right? We have our lamp, and that is so bad. We have our lamp, then we have our monochromator, the cuvette, and then the detector. Well, if we start to fluoresce at a different wavelength than what's being put into it, then there's no quote unquote noise to disrupt you from seeing that. All you're seeing is you're just seeing, okay, something's happening at 330 nanometers, for instance. We are not shooting that through it, so it has to be fluorescing. So the molecule is there. That's very important. Um, it's a very important thing about fluorescence. Now let's talk about what happens in fluorescence exactly. Okay, so this is a general diagram to help us describe fluorescence. So what happens is we have our ground electronic state, which is where our unexcited electrons are going to be. And then we have our excited electronic state, which is where electrons will end up after they absorb a photon. So let's talk about this in steps. So first, we start in the ground state, and then we are excited. In this period, we are absorbing a photon, and then we're going up to the excited electronic state. And this excited electronic state has a different vibrational state of molecules as opposed to the ground state. So the vibration is going to be a little bit different. Two, our next step, we have relaxation to a lower vibrational state. So relaxation, but we're still in excited state. And then finally, what happens is we fully relax. Relax back down to ground state. Okay, so what's happening here is we're absorbing some photon of light, so photon, with a short wavelength. We're observing a photon with a short wavelength. What happens is when we relax from this higher part, so this higher vibrational part, to this lower vibrational part, we're losing a little bit of energy. And then when I jump all the way back down to my ground state, then I'm going to release a photon with a longer wavelength. And that's how fluorescing works on a very general scale, very simple scale as well. But you'll see that fluorescence isn't always automatic. There's like chemical ways to store the energy and then wait for fluorescence to occur later, which is why sometimes you'll see the algae like at night that's fluorescing. But yeah, I think this covers everything from this week. So good luck studying, and I'll see you in the next video.